Hi students, good evening. So today we are discussing the last topic of our econometrics course. That is the topic of limited dependent variable. This is an interesting case. Uh, Although this problem we don't encounter frequently, but there are occasions while undertaking econometric analysis we face a situation which we put under limited dependent variable. Let me explain with couple of examples. So if you are trying to assess how the income, market rent, number of family members in a family determine how much an individual or a household want to spend on buying a house. Okay, so then you face a typical situation when you collect data on these households or individuals on how much they spend, how much they have spent on buying an apartment or house, and what is their level of income, what is the market rent, and the family size, and any other explanatory variable which you think influence their decision on how much to spend on buying an apartment or house. Then you face a typical situation where for a set of observations which I can say a subsample in your sample will have might have purchased houses or apartments. So for them you have some figure, like some household has spent 50 lakhs or 60 lakhs or 1 crore on housing, buying an apartment or a house. So you have that information, and of course you have information on all the explanatory variable which you are thinking that will influence the decision to buy spend on housing. Then within your sample you will have another set of individuals or households who have not bought a house, okay, or have not bought an apartment. So then for these households you may have all information on the explanatory variables for this subsample, but you will not have information on how much they spent on housing, because you'll basically assume that to be zero. If they have not spent on housing, you will assume that zero. So this is one case where if you plot the observations in your xy plane, say assume there is only one explanatory variable which you are considering, and say that is income, which you put on the x-axis, and how much they spent on buying a flat or house on y-axis. Then you may have two sets of observations like this. Maybe the green dots, the green circles, small circles, so scattered here. For these households you have information both on how much they spent on housing and information on their income. Okay, so they are appearing in the xy plane, where the values are non-zero. Okay, both x and y are non-zero. But you have some households here which are marked as a small red cross. So here for you have positive, they have positive income, but because they have not bought any flat or house, so that amount of expenditure is shown as zero, right? So this is a typical case of limited dependent variable, which you call a case of censored data. The data is censored or hidden. See, somebody has not bought an apartment or house, doesn't mean that he or she doesn't desire to spend something on house. Okay, so that desire, how much a household depending on their income wants to spend on housing, is not observed, it is hidden for those households who have not bought house, right? So if you are trying to run a regression with this type of data, where for some observations the value of dependent value variable is zero, and for some observations it is non-zero, then it is a case of censored data or limited dependent variable. So what is the problem here? See, basically there can be some latent index in the mind of the individual or households who is buying, deciding to buy a house. So that latent variable or index should vary with income. So assume if there is a positive relation, as income increases, this index, which basically captures the desire to spend a particular amount on house, on buying an apartment, should increase. Okay, but because we have some observations where we are observing zero values, the actual latent variable or the hidden variable here is not observed for those households who have not bought house. Okay, we have many examples like this in economics and finance, which we come across, where we encounter the problem of limited dependent variable. Another example is, I can give related to the when you are analyzing saving behavior of individuals. So if you assume that the saving behavior of an household or of a household or an individual depends on the income, family size, demographic factors, all those things, what is specified, guided by economic theories on saving, then you'll observe that you may have information for all your households on the explanatory variables like family size, income, demographic factors, etc. But then for some households who are actually reported savings, positive amount of savings, for them you will have saving data. But for some households who have not reported positive amount of savings, perhaps you are assuming their saving amount is zero, so you are giving a zero figure for their dependent variable. But actually these households, if we assume that income has an impact on saving, if we assume the demographic factors have an impact on saving, so depending on the values of the explanatory variable, there could be some latent values or latent index on saving for even those households who have not reported positive saving, right? Now if we are applying standard multiple regression model, which we discussed in earlier part of our course, to this type of problem, we encounter some serious problems. The thing is, the way these scatter plots are, what you can see is, from some observations y value is 0, for some observations y value is non-zero. Okay, now if you run the regression ignoring these observations for which the y value is 0, then obviously your expected mean value is non-zero. Okay, so one important classical linear regression model assumption is violated. So if your mean value expected ui is non-zero, then you encounter the problem of biasness of your OLS estimator, and even your OLS estimator will be inconsistent, right? Now the other way of looking at it is, see, now let us mathematically specify this type of a model where yi, okay, the amount of spending on housing is given by this function, and this is observable for those households who had spent some positive amount on buying an apartment. Okay, now for those households you didn't get, those who didn't buy an apartment or house, for them the value of yi is 0. Okay, so you can think of some latent index like ii. So when this ii is say below some threshold value, like here actual spending is 0, it cannot be negative 0, so in that case your yi is taking value of 0, and when it is positive it is equal to that positive amount of spending. So this has some similarity with the Tobit model which we discussed earlier. So in the Tobit model, only difference is yi was taking the value equal to 1 when somebody bought a house, when that latent index which we discussed, that is basically greater than some threshold value I star, and otherwise it was 0. So it was, the y value was either 1 or 0, binary. But now the yi value is actual yi if some positive amount of spending is carried out. That is, if the person has, or the individual or the household has bought an house, and the yi value is 0 when he has not bought an house, right? So then, assuming there is a II, latent index here, which is a function of income. I'm assuming, I'm taking just one variable for easy explanation. So I'm assuming this is a function of xi, which is income. So II, that index is a function of, is equal to alpha plus beta xi plus ui. Okay. So now, if we assume that u, the stochastic error term here, follows a normal distribution, from that we can basically derive a standard normal. As you assume that ui follows a normal distribution with mean 0 and variance sigma square, then we can construct a variable z, which is u over sigma, which will be a standard normal. Okay, so basically, if what I'm trying to say, if u follows a normal distribution with mean 0 and variance sigma square, then we can construct z as u over sigma, which will be a standard normal. Okay, standard normal random variable. Now, based on z, I can define fx as the probability, fz as the probability density function. I'm writing this as the small f. Okay, so z is that standard normal which we discussed, which we constructed as u over sigma, and fz is the probability density function, and then capital fz. Here it is the small f, here capital F. Capital Fz is the cumulative, the density function. So how to define the cumulative density function? We know the probability of z being less than equal to some value. Here it is small z. So that basically defines the cumulative density function. Now we discussed we can apply, we should not apply OLS here, given that you have some values 0, some values non-zero for y, and we are if you are applying OLS, we'll get biased estimator. Okay, a biased estimate for the sample population parameters. So that's why we are applying maximum likelihood and procedure. So for applying maximum likelihood procedure, let us take this set of observations for which our y value is observable. Okay, there is a positive expenditure spent on buying an apartment or a house. So then the joint probability distribution for those households I can denote as P1 as pi running from I from 1 to m. I'm assuming there are m households for which we have information on how much they spent on housing. So they have bought a house or an apartment. Okay, so this is their probability joint probability density function. So here this is basically u, you see, yi minus alpha minus beta xi I missed here. So this is basically, the numerator is u, the denominator is sigma. So this basically gives the joint probability density, which is basically product. This pi stands for the product sign, equivalent to sigma. Sigma is for summation operator, pi is for the product operator. And so for the first set of households, that is the first subsample for which we have observation of yi greater than 0, these households are bought house. This is the joint probability density function. For those households who have not bought house, so we have observed 0 for their y. Okay, for those households we can define the their joint probability density function this way. So P2 is a product of P, where ui is less than equal to alpha minus beta xi. So this basically we can observe from here. This is basically y minus that u, right? So y value is 0, so it is minus alpha minus beta xi and sigma in the denominator. Now the joint probability function for the entire sample, which includes sample 1, sample 2, let me denote as L, which will be product of P1 and P2. P1 and P2 the way we define now. Now if you observe the structure of P1 and P2, you'll appreciate that L is now it is in non-linear in alpha and beta. So our OLS application requires that the exponent of the popular, our parameters, say, intercept and slope should be 1. Okay, those should be linear in parameter. The model should be linear in parameter. Now you have these joint probability density functions where they are non-linear in alpha and beta. Okay, so obviously we cannot apply OLS, and we'll be applying maximum likelihood estimation techniques, which we have been discussing for last 2-3 lectures. So by applying maximum likelihood estimation technique, we can estimate the model. So it is clear your Y values are like actual expenditure and zeros, combination of actual expenditures and zeros, that actual YI is equal to YI for those who bought house, is equal to 0 for those who didn't buy the house. And you have all the expenditure variables. Here we consider only income. You can consider other relevant expenditure variables also, and then you can apply OLS to estimate this model. This model is popularly known as Tobit model. The noted economist and Nobel laureate James Tobin had applied this to analyze behavior of how much people spend on automobile. So I think that is the the base work based on which this method was or the modeling was further improved by various authors, and one can apply maximum likelihood techniques to estimate this model. Now, one important issue is regarding estimation and diagnostic checkings. See, for estimation, of course, we are applying maximum likelihood. The interpretation. See, the slope coefficient normally gives us the marginal impact of increase in explanatory variable on the dependent variable. Okay. Here, for us, the dependent variable is actually the latent variable yi, which is we are not observing for those households who didn't buy a house, right? So if I estimate the slope coefficient to be say 0.4 for the income, this suggests that when income is increasing by unit, like if the unit of measurement is 1000, so if income is increased by 1000, then that latent variable, which basically represents the desire of the household to spend a particular amount on housing, that increases by 0.4, whatever units that is expressed in. Okay, so but what we are interested in to know what is the impact on actual spending on housing, not on the desired spending on housing, right? So we have a difficulty to directly get the impact on actual expenditure on housing when income increases. We don't get it, we're not able to get it directly. But depending on the sign of the coefficient and the of course testing its statistical significance and the diagnostic checks, we can infer whether there is a positive impact or a negative impact. In terms of magnitude of impact, we'll have some idea, because this slope coefficient basically captures two things. The slope coefficient captures the impact, marginal impact on the desire to buy a house, okay, that latent variable yi star, if I say, and the probability of observing that latent variable. Okay, so it is a product of these two things. Given that probability will vary between 0 and 1, it is always less than 1. So in terms of magnitude, we can say the marginal impact on actual expenditure on housing will be lesser than the marginal impact on the latent variable, which is desired to spend on housing. Okay, so that there we have some difficulty, but we can of course assess whether there is a positive impact or negative impact, or whether that coefficient is significant. So generally for testing the significance, we will not apply standard t test here. We'll apply z test, which is used for large sample. And then for checking the goodness of fit, we will not apply the standard R square. We'll apply some pseudo R square, which is used for maximum likelihood estimates. And even of course you can take some sort of the correlation coefficient between the actual values and the estimated values, and then sort of take their square. You can also get some idea about the goodness of it. but standard econometric software packages give you the pseudo R square when you are estimating a model applying maximum likelihood technique. So that way you can use those indicators for diagnostic check. So I think with this we'll conclude our course on econometrics. So a quick revision I'll do what we covered. Basically we started with discussing the nature and scope of econometrics as a subject. So we discussed that this is a subject which is some sort of a combination of economic theory and statistical methods and mathematical tools. Basically econometrics means economic measurement. So when theory suggests how the qualitative aspect of a relationship among economic variables, or qualitative aspect of explaining certain behavior, like behavior explaining consumption expenditure pattern of a household, or trying to explain prices given the demand and supply, etc. So the theory specifies the qualitative aspect of the relation. Econometrics, by using economic theory, collecting data and applying mathematical statistical tools, which is a combination. This is a special technique which is used for measuring economic relations. And in terms of scope, we said basically there are three important usefulness of the study of econometrics. One is, of course, we are measuring relation. So then after measuring economic relation, we can sort of provide empirical support for assessing the validity of an economic theory. So for example, if we are talking about the Keynesian psychological law, if it suggests that the marginal propensity to consume, MPC, is supposed to be greater than 0 and less than 1, if we collected data on disposable income and consumption expenditure on a regression, and we found that MPC is say 1.2, then that suggests perhaps there is some problem with the economic theory, which is this particular economic theory, or there is a need for improvement of economic theory. So this way the econometrics, by estimating economic relations, provide empirical support towards strengthening the validity of an economic theory. Or if the theory is adequately not supported by empirical evidences, perhaps this provides scope for further improving the economic theory. So that way provides feedback for improving the economic theory itself. And then finally forecasting, as we discussed, any economic decision, whether it is a policy decision by a public authority like Government of India or Reserve Bank of India, or a decision by a private corporate, most of the economic decisions have a forward looking impact. So for example, if the Reserve Bank of India is raising policy rate today, it is likely to have impact on the market interest rates in future, maybe 1 week ahead or 1 month ahead or maybe 1 year ahead, and consequently it impacts the credit flow or consumption expenditure, investment expenditure, which is financed by bank loans, and finally aggregate demand over time. So given that the policy action today may have impact on the economy maybe 6 months ahead, or 1 year ahead, there is a need for focusing about the future, some sort of projection about the economic variables for the future. Say if I assume that monetary policy is used for controlling inflation, and if correct econometric model is used to forecast that in inflation 1 year ahead will be 8%, which is beyond the tolerable limit of Reserve Bank, then policy action need to be initiated 1 year ahead, given that the impact will be having 1 year lag. So 1 year ahead, the policy action need to be initiated by raising interest rate, compressing aggregate demand, so that inflation will be brought down to its tolerable limit, maybe below 6 from 8, what is likely to happen without policy action. So the precision in projection is quite essential. If the precision is correct, without policy action, inflation is supposed to be, precision in projection I'm talking about. So if inflation was supposed to be 8% without policy action, and the Reserve Bank took action, brought it down to 6% or 4%, then it is good. But if inflation, our projection is incorrect, that we incorrectly projected that inflation is supposed to be at 8% 1 year ahead, whereas actually it is supposed to be maybe 4%, then any monetary tightening will bring inflation further down from 4% to maybe 1%, which is not desirable. So, correct projection, perfect projection is of course not possible. Perfect forecasting is of course not possible. Even if you apply the most sophisticated econometric model with the best mind, the best econometricians, but what matters is precision. So if projections are more precise, then perhaps policy actions will be more appropriate, whether it is a private sector decision, a private corporate decision, or a public authority decision. So these are important uses of econometrics. Then how econometrics differs from a standard mathematical model. A standard mathematical model is deterministic. Okay, it doesn't take into account the randomness in the decision making of an individual or thinking of behavior of an individual. Say like there may be 10 households with income of 50,000 each. Now if their income is increased by 1,000, the increase in consumption expenditure of these 10 households will not be uniform. For some households increase may be 900, for some household increase may be 100. So the mathematical model basically suggests there is a uniformity there is in the impact on the dependent variable due to change in exponential variable, which econometric model improved by introducing the stochastic error term. Okay, and this stochastic error term takes into account the randomness in the behavior of individual. The stochastic error term also takes into account certain things, like if there is a measurement error in measuring the observations and the variables which are using, those things also are taken care of. If there is a misspecification in model, that also part of that is captured in the stochastic error term. And we discussed this stochastic error term is very critical for our econometric model. We discussed that based on certain properties of the stochastic error term and of course the econometric model, if these assumptions are satisfied, then Gauss-Markov theorem suggests that our OLS estimates will be best linear unbiased estimator. See, basically this issue comes into our discussion because generally when you are estimating an econometric model, we are using a particular sample. Okay, and this sample is drawn from a population, and in economics and in social science we are not fortunate to have all observations of the population at our hand. We cannot obtain that, so we have to rely on a sample, and based on the sample estimates applying OLS method we have discussed already, so I don't want to spend more time on this. So if this OLS applying OLS method, we are estimating the sample coefficients for say slope coefficient, intercept coefficient, etc. Then if the Gauss-Markov theorem suggests that if certain important assumptions are satisfied, then these sample estimates are best linear unbiased unbiased estimators of the population parameter. Okay, so that gives us comfort. Even if we are estimating for the sample, most likely we are able to make conclusion about the population parameters, and of course related issues on hypothesis testing and the confidence interval and all we discussed, basically to ensure that our opinion about the population parameter, our conclusions about the population parameter are more precise. So in this process there is a likelihood of committing type 1 error or type 2 error. We cannot avoid both. So if we are increasing type 2 error, type 1 error will be less. If we are trying to control type 2 error, then type 1 error will be less. So within that we basically try to fix type 1 error which is more serious at a particular level and try to minimize type 2 error whatever maximum possible. So then these assumptions were related to, as I said, mainly on behavior of the stochastic error term. One assumption was stochastic error term, mean of the stochastic error term should be equal to 0. And then there should be homoscedasticity, there should be autocorrelation, no autocorrelation, there should not be high multicollinearity, and there should not be any the covariance between the experimental variable and stochastic error term should be equal to 0. And yeah, these are important assumptions of classical linear regression model. If these assumptions are satisfied, then we are comfortable that our mm, sample estimates are the best on linear best best linear BLUE, best linear unbiased estimator of the population parameters. But in practice, when we are estimating an econometric model, generally we are not that lucky that all these assumptions will be satisfied. At least one or maybe more than one assumptions will be violated in any case you are taking up. Then we discussed that if there is a problem of autocorrelation, what are the consequences? First, how to detect that. If there is autocorrelation, what are the consequences and how to find some remedy. So autocorrelation, heteroscedasticity, multicollinearity, all those cases we discussed. How to detect the problems, how to what are the consequences, and then what are the remedial measures. Then jumping from single equation to multiple equations model we took off because many times the economic behavior is not a partial behavior, like say for example market equilibrium. In market, the equilibrium quantity, equilibrium price is determined through the interaction of demand and supply. So if I'm estimating a single equation like a demand equation, it is part of the story. Or if I'm estimating the supply equation, it is part of the story. And wherever when there is a simultaneity, there is endogeneity. If you are ignoring this issue and estimating a single equation, then there are adverse consequences. So we learned various simultaneous equation techniques on how to address these issues where there is a simultaneity and estimate simultaneous equations models. Then finally, we came to the last section where we discussed about possibilities of uh, qualitative explanatory variables or qualitative dependent variable. Certain variables can be in our econometric analysis can be non-quantitative, non-numerical, like maybe gender, uh, you know maybe the credit rating, or the decision to buy a house or not, all those things. So then we discussed how to use dummy variable analysis to deal with the problems where a right hand side variable is qualitative in nature. And last couple of lectures we discussed how to deal with a problem where the left hand side variable is qualitative in nature, which we called as the probability model. And finally we discussed about the limited dependent variable case. Okay, so that concludes our course. And I know actually particularly the last module which we discussed online, you might have difficulties. One, uh, discussing these courses online is a new experience for me. And a course like econometrics where we are not able to use a board to derive things, will have some issues and confusion. Maybe you have not got clarity on certain issues. But given the constraints, we tried our best.